Hi, welcome class. Today we're going to be looking at binomial distributions. So this is the third lesson in the series. What we want to be able to do is, first of all, we want to know what a binomial distribution is, but we also want to use this to calculate probabilities for a variable that are involved in binomial experiments. We also want to be able to calculate the mean, variance, and standard deviation for a given random variable, just the same way that we did in lesson 2 when we calculated these same quantities for generic probability distributions. This time we're focused specifically on the binomial. So what is a binomial distribution? So bi, just like in the word bicycle, means two. In the case of bicycle, that means that you have two wheels. The word nomial means name or category. So name or category. In the case of binomial, if you put them together, well, that just means you have two names or two categories. So here we have two categories, right? So in this example, we have an experiment set up, and we call it binomial experiment because we only have two outcomes from this experiment. We'll talk about more of that later when we do the requirements in a little bit. When you do an experiment, each repetition of that experiment that you undergo is called a trial. Now, in order for something to be called a binomial experiment as opposed to just a generic probability experiment, is that it has to satisfy the following four requirements. So the first requirement is that the number of trials has to remain fixed. So if you're doing a coin toss, for example, if you're tossing two coins, then that can't change. It can't change from 2 coins to 3 coins all of a sudden. It has to be the same number of trials, the same thing going on. As far as the second requirement is concerned, each trial can only have two possibilities. So you can only have two outcomes, hence why we call it a binomial. These outcomes can be considered either success or failure. We'll talk a little bit more about what success or failure refers to in about a minute. So the next requirement, if you will, is that the outcomes of each trial must be independent of one another. We call the word independent. Whenever we calculated probabilities in Chapter 4, we talked about independent outcomes and dependent outcomes, or independent events and dependent events. Remember that an independent event means that the probability that one happens does not impact the probability of another event happening. That's why they're known as independent. So for example, when we are drawing cards from a deck, if you choose the first card and you hold on to it, and then you choose another card, well, those events are now dependent because you change the chances of getting another card whenever you held on to the first card. If you were to put the card back into the deck and then reshuffle the deck, then the probability of getting a particular card will be the same no matter what, because all the cards are now intact and in the deck. So in this case, for this requirement, they cannot be dependent. So the last requirement is that the probability must be the same for each trial. So it must remain constant. So for example, in a coin toss, the probability of getting heads or tails is 0.5, and that doesn't change. It remains constant. So what does the word success or failure mean in this context? So success doesn't literally mean success, as in something good has occurred, or failure doesn't literally mean that something bad has occurred. It's just saying that success or failure depends on the context. It depends on the kind of experiment you're doing. So for example, if you're doing an experiment on the number of tails that you get from tossing 2 coins or tossing more than 2 coins, then you're going to record the number of tails. And success in that experiment means getting a specific number of tails. And failure in that case would be getting heads. So in that case, failure is getting heads, success is getting tails. But you can also reverse it depending on what kind of experiment you're doing. So success or failure is dependent on the context. Now, as far as the outcomes, if you're talking about combining the outcomes with the probabilities, well, we call that a distribution. So if you're doing it for a binomial experiment, we call that a binomial distribution. Remember that for a probability distribution, you can set it up with the XP chart with your probabilities and your outcomes. And in this case, we're only going to have 2 outcomes and then basically 2 probabilities. All right, so now we're going to decide in the following problems whether they're binomial or not. And if so, or if they're not binomial, then state the reason. So basically, we're going to be using these 4 requirements to help us with the problem. So part A is selecting 20 university students and recording their class rank. So in that case, we're talking about class rank. So we can have multiple categories here, right? We can have freshmen, we can have sophomores, we can have seniors, we can have juniors. We can even have graduate students, because in a university you have undergraduate students and graduate students. So therefore there's more than 2 categories here. Therefore it fails one of the requirements for it to be called a binomial experiment, which means that it's not a binomial experiment. It fails the second requirement. Each trial can only have 2 possibilities. So in this case, this is a no, because there are more than 2 outcomes. Now let's look at B. So we're selecting 5 students from a large school and asking them if they are on the dean's list. In this case, this is a yes or no question, right? You ask them, are you on the dean's list? And they would reply yes or no. So in this case, this would be a binomial experiment. You only have 2 outcomes, yes or no. So yes. And the students are independent from one another, right? So it doesn't matter what student you pick, they're still going to be independent from the other student that you ask. One student might say yes, one student might say no, but they're independent from each other. The probability of success is constant. In this case, the probability that the student says yes or no may be like 50%, depending on the scenario. And then each trial, you only have 2 outcomes. And then if you select a fixed number of students, here we only have 5 students, so we have a fixed number of trials, 5 students. All right, so in this case, this is a yes. 2 outcomes, and I'm just going to put a little note here. The 2 outcomes here are yes or no to that question. Part C is asking, so we're drawing 5 cards from a deck without replacement, and we're recording whether they're red or black cards. Well, in this case, we do have 2 outcomes. We have a red and a black card, or a black card, so that those are 2 outcomes. So red or black. So we have 2 outcomes. But however, you want to zoom in on the fact that it says that you're selecting it without replacement. When you're not replacing the card, that changes the probability of drawing the next card. So therefore, these are dependent. So remember, one of the requirements is that it has to be independent of one another. So this is not the case. So this is not a binomial experiment. Okay, so is that key? If it said with replacement, then this would be independent and we should be good to go. All right, so this would be no. The events are dependent since the cards are not replaced. All right, part D, we're selecting 5 students from a large school, asking them if they're on the dean's list. Actually, we already did that in part D, did we not? Oh, okay, so we actually did this in part D. So I skipped ahead. I skipped B and I went straight to D. So let's do B now. Selecting 20 students from a university and recording their gender. So in this case, you only have 2 genders. You have male, female. We're assuming that this is a typical scenario and not in any way modified. So just a conventional notion of gender, so male, female. And then in this case, this would be binomial, 2 categories. We have a fixed number of trials, 20 students. And each student is expected to be independent from one another. So this would be a yes. And I'm just going to say you can have male or female. All right, so now we're looking at the last one, which is recording the number of children in 50 randomly selected families. So in this case, well, if you ask a particular family how many children they have, well, they could say they have 0 children, or 1 child, or 2 children, or even 5 children or more. So in this case, you have more than 2 responses, so more than 2 categories. So this is not a binomial experiment. So no, you can have more than 2 categories for the answers. All right, so now we're looking at the other page on the back. So now, if we were to calculate probabilities, now that we know what constitutes a binomial experiment, or we should know like what the requirements are in order for a probability experiment to be called binomial, we can now proceed to calculate the probabilities. So we're going to use this formula for the probability. All right, there are a couple different variations of this formula, and I'm going to write them down as well. Remember that this part with the factorials, remember that this is the factorial symbol. And what that means is that you're going to take a number like say 9 and then multiply it by 8 and 7 and 6 and 5 and 4 all the way to 1. So you're getting less and less and multiplying those numbers. So that's what factorial means. If you recall, this is actually one of the formulas from the previous chapter when we talked about counting. This is actually the combination. So we can rewrite this in terms of combination. So that's n combination x. This is n choose x. And then we can replace that with the combination and makes life easier. It makes it look nicer. All right. The other symbol for the combination, if you remember, is the parentheses with n choose x like that. That's another way to rewrite the combination. You can use whatever symbol you prefer. But just keep in mind those are different ways of writing the probability formula. Okay, so these are all the same formula. They're just written in different ways. Now let's talk about the variables. So the n stands for the number of trials here. So this is the number of trials. The x here is the number of successes. So in like if you're doing an experiment on where you're tossing 2 coins and you're looking for the probability of getting 1 tail, well, your number of successes in that case is the number of tails, which is 1. So this is the number of successes. All right, and then the probability here, this P right here stands for the probability of success. Again, success is how you define it based on the experiment. So this is the probability of success. The Q here is the probability of failure. Remember that if you know the probability of success, you can find out the probability of failure. So if success is 20%, then failure would be 80%. So you know one if you know the other. All right, so those are the variables. Those are where you need in order to be able to calculate the probabilities. So let's look at how this works. So let's look at the following problem. So we have a survey found that 1 out of 5 Americans, we can rewrite this right here, 1 out of 5, says he or she has visited a doctor in any given month. If 10 people are selected at random, so here we're doing this randomly, and we're looking at 10 people, so that means that's our number of trials. So the number of trials is 10. So if 10 people are selected at random, find the probability that exactly 3 will have visited a doctor last month. So in this example, it's a binomial experiment because they can either say yes or no to that question. So did they visit a doctor or did they not? So this is binomial, so you have 2 outcomes. In this case, the number of successes, so the success is determined, is basically, so quote unquote success is, did they visit the doctor, all right? So this is success right here, visited a doctor last month. So that means the number of successes, or X, is 3. All right, so exactly 3 people visited a doctor. All right, what's the probability of success then? Well, now that we know that success is visiting a doctor, well, it says here that 1 out of 5 people visited a doctor in a given month. So that means the probability of success, little p, is 1 out of 5. Which means that we can find the probability of success. So if we know probability of failure, if we know that success is 1/5, then that means we can find the probability of failure is going to be 4/5. Remember that they had to add up to 1 altogether. Now we should be able to have everything that we need here. We can plug it into the formula. We have n, we have x, we have p and q, so we should be able to plug it into this formula. So I'm going to use the combination formula for this one. So we have p of x equals, and then now we can go ahead and plug in the numbers. So you're going to plug in your n, so n is 10. Combination, so we're doing 10, choose, we have 3 successes. So this should be 3, so replace this with a 3 because we're doing the probability that we have 3 successes. Equals 10, combination 3. Then we're going to multiply by our probability of success, which is 1/5, and then raise to the x power, that's what it says here, the x power, which is 3 successes, times probability of failure, 4/5, raised to the, so it says n minus x power. So that means n is 10, so 10 minus 3 power. All right, so I'm going to simplify this a little bit more. So we got 10 combination 3, 1/5 to the 3rd, 4/5 to the 7th. So now we have to be able to calculate the combination. So you can type this into the calculator, or you can type it into the formula. So I'll just type it into the formula. I'll just kind of do that on the side, but you can always do this on the calculator. But I'll do it on the side just so that you know how it's calculated in case you want to do that. Okay, so we got 10 factorial over 10 minus 3 factorial. This will also help you review factorials if you forgot how to do them. And then x factorial. All right, so 10 minus 3 is 7. So I got 10 factorial over 7 factorial times 3 factorial. Remember that we have 10 factorial is 10 times 9 times 8 times 7 times 6 all the way over. So I'm going to replace this, I'm going to rewrite this as 10 times 9 times 8 times 7 factorial. And I'm not going to continue to 6, 5, 4, 3, 2, 1 because I got a 7 factorial here. So that's why I'm stopping it short there. So these cancel. And then 3 factorial is 3 times 2 times 1. So I'm going to replace that with 3 times 2 times 1. And then I'm going to do the math here. So 10 times 9 times 8. So this is going to be 720. And then 3 times 2 is 6. So 720 divided by 6, which is 120. So now I can replace that for my combination. Okay, so now I got 120, 1/5 to the 3rd, 4/5 to the 7th. And at that point, you can go ahead and plug that into the calculator, and you will get your answer. So in this example, we will get approximately, let's write it over here, approximately 0.201. All right, so now let's go ahead and do the next problem. So a survey from Teenage Research Unlimited found that 30% of teenage consumers receive their spending money from part-time jobs. If 5 teenagers are selected at random, find the probability that at least 3 of them will have part-time jobs. All right, so 30%, that can be expressed as a fraction or a decimal. So I'm going to rewrite that as 0.3. So find the probability that at least 3 of them will have part-time jobs. That means that those that have part-time jobs, So you have two categories. You can either have a part-time job or you don't have a part-time job. So in this case, success means has a part-time job. All right, so that's our definition of success in this experiment. So you either have one or you don't. So that's two outcomes. The probability of getting a part-time job is 0.3 according to the research. And our number of trials is 5 because we're looking at 5 teenagers. Well, the x here, the x is going to be at least 3. So we're going to rewrite this. So here in this example, x is greater than or equal to 3. So why is it greater than? Because it says at least. At least means minimum 3. So that's my x. So in this example, we have p and x. Let's go ahead and write out q. So if we know that p is 0.3, then q has to add up to 1, so it has to be 0.7. All right, we should have everything that we need for this problem. So now we need to do the probability that x is greater than or equal to 3, which means we have to do the binomial distribution 3 times. We need to do it we need to do it at least more than once. So we need to do it for x is equal to 3, for x is equal to 4, and then 5. So we need to do it for probability that x is 3. We need to do it for the probability that x is 4. And we need to do it for x is equal to 5. Remember that we stop at 5 because we only have 5 teenagers selected at random. So that's why we stop at 5. So we need to do the binomial 3 times, which I know can be kind of tedious. So we're going to show you in a little bit a shortcut of finding all the binomial probabilities. But in the meantime, for this problem, we're going to actually calculate it. And then for number 4, we're going to actually show you the quick way using a table. All right, so we're going to go ahead and plug this into the formula, get you used to it. So we have combination. We have a total of 5 people chosen 3 at a time. Probability of success is 0.3 raised to the x power, which is 3. Probability of failure times you do raised to the n minus x power, going straight to the formula. So that takes care of this part. Now we're going to do this guy. So we're going to repeat this, but with 4. All right, and then we're going to do the last one. So that's the box is this one. All right, now let's do the last one for 5. All right, so now you just got to put it into a calculator and get an answer and then add them together. So when you do this, you're going to get, let me tell you what the probabilities are. So for this one, it's going to be 0.132. The second one is going to be 0.028. And then the third one is going to be 0.002. And then you do all of this at once. You add them together, you get 0.162. All right, so that's your total probability. All right, so now let's show you a quick way of actually getting these numbers by utilizing the fourth problem. All right, so now if we look at the fourth problem, it says that we have 5% of Americans are afraid of being alone in the house at night. If a random sample of 20 Americans is selected, find these probabilities by using the binomial table. So that's what we're going to use. So in class, I will see if I can print out the binomial table for you guys. And that's Appendix A on the ebook. So this is how the binomial table looks like. It's Table B in the book. And basically, they give you the number of trials. So you look up your number of trials. So if you have 5, then you're going to go to n equals 5. And then you look up the number of successes that you want to calculate it for. So let's say you have 5 students, and you wanted to see if 3 said yes to your question. So then 5, 3 successes, and then you want to look at the probability of success. So is the probability of success 0.5, 0.3, whatever. And then you look that up, 0.3, and then that's your binomial probability. It's as simple as that. That's all you had to do. Once you know those 3 things, you should be able to calculate your probability. So let's show you how to do this in this problem. So it says here that we're looking at 20 Americans, so that's my n. N is equal to 20. So we're going to need to go to the very end of the table with n equals 20. All right, so let's go ahead and identify the rest of this. So it says so basically success is being alone, being afraid of being alone at night. Okay, so that's considered success for us. All right, which is, like I said, it's not literally success. It's just in this experiment that's success. And then the probability of that is 5%, which is 0.05. So that's the probability of success. All right, and then, so A, there are exactly 5 people in the sample who are afraid of being alone at night. So this is my x. So x is equal to 5. So for part A, we're really looking at the probability that x is equal to 5. So like we said, once we know these 3 things, we should be able to calculate this. So we're going to go back to the table. All right, so I'm going to go to the very last portion of the table where it has n equals 20. So I got 20 trials, right? And I'm going to now begin to look this up. So n is 20. We said that x is 5. So x is 5. So we're looking at here. And then the probability of success is, we said it was 5% or 0.05. So then we go ahead and look that up. So we got 0.05 here. We're looking at 5 successes for 20 people. That's the probability, 0.002. So now we know what that is for part A. And it's as simple as that. That's all you have to do in order to get that probability. So that answer is finished. So now, or that part, so now part B, there are at most 3 people, which means that the greatest you can have is 3. So you can have 0 people, or 1, or 2, or 3. So probability at most, so less than or equal to, which means you can have 0, 1, 2, or 3. So you're going to have to find out all these probabilities. So instead of plugging into the formula, we use the table. So we got 20. We're looking for 0 successes, probability 0.05. So that gives us 0.358. So that's this probability right here, 0.358. Next one, 1 success, 0.377. And then the last one, or next to the last one, we got 0.189 and then 0.060. Add those together and you get 0.984. Now we're going to do the last one, part C. There are at least 3 people in the sample who are afraid of being alone at night. So at least means greater than, right? So greater than or equal to 3, which means we need, well, we have 20 Americans, right? So we're going to have to do this for 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10, all the way to 20. But that's a lot of work. Even with the table, that's a lot of work. So what we're going to do is we're going to do the opposite of that. So the opposite of getting more than 3 is getting less than 3. Remember that the opposite or the complement in the original event had to add up to 1. So we know that to get the greater than, we can do 1 minus the less than, and that will give us the greater than. Okay, so what we can do is just calculate this guy and then do -1, and then we get our answer. So we're going to do 1 minus, now we need to do the probability of 2 plus the probability of 1 plus the probability of 0. And that will give us our answer. So we need to find this on the table. So we said 2 was 0.189, and then 1, and then 0. So we can go ahead and plug that in. So we add those together, subtract from 1, and then we get our final answer. So we'll go ahead and write down the answer for that. So for C, you should be able to get 0.076. All right, and that's your answer for that part. So table makes it so much easier. Now we're going to go to the next page. Now, next thing we want to focus on in this lesson is how we actually calculate mean, variance, standard deviation. So in order to do that, we're going to use the following formulas. All right, I already provided them to you. So let's go ahead and go to the example. So we have a coin is being tossed. You're tossing it 4 times. So our trial, we have 4, our n equals 4 in this case. So we have the fixed number of trials. Find the mean, variance, and standard deviation. So now all we got to do is find the mu first. So the number of trials is 4. What's the probability of success in this case? Well, success in this case is the number of heads. So success is getting H, so getting heads. So in this example, getting the probability of success in this case is 0.5. Probability of getting heads is 1/2. So we can multiply this by 0.5 and we get our answer, which is 2. So that's it for the mean. Pretty easy, pretty simple. Now we need to find the variance. So we're going to do sigma squared equals n times p times q. Q is failure. So in this case, remember failure, if success is 50%, failure is 50%. So we have here 4 times 0.5 times 0.5, which gives us 1. That's it for our variance. Now standard deviation, all you got to do is take the square root of the variance, which is square root of 1, which is 1. All right, so that's it for that example. Not too bad. So on average, if we keep doing this experiment forever and we average the results, we'll get 2 heads. And then on average, it seems that the spread is about 1 on average. All right. So number 6, we're going to do the same idea here. So it says reported that 2% of all American births result in twins. If a random sample of 8,000 births is taken, find the mean, variance, and standard deviation for the number of births. So we need to find n. In this case, we're looking at 8,000 births. All right. Now this is a binomial because you can either have twins or you're not twins, right? So that's 2 categories. And the probability of resulting in twins, which is in this case success, is 0.02. So that means that mu is equal to, the mean is 8,000 times 0.02, which in this case is 160. Sigma squared, so we need our 8,000 twins, or 8,000 births, times the probability of success. So if we know success, we know failure. It has to add up to 1, so this has to be 98%. So we multiply by that, and we get